Hey folks, it's Mr. Ray here with our next lesson, grade 10 academic math. We're starting the next unit, um, and it's actually related to the previous unit when we did quadratic relations. Um, we're going to see in a future lesson how it links back very nicely, but for now we're going to be talking about quadratic equations. So what's a quadratic equation? Well, anything that's a quadratic relation has a quadratic equation. Obviously, it's the same type of relationship, so um, the equation comes from the relationship. So, what makes the purpose of today's lesson, in a nutshell, is by the end you should be able to look at an equation of a quadratic relation and understand why that equation is quadratic. You should be able to look at a graph of a quadratic relation and know that it's from a quadratic relation, and also a table of values. Okay, so uh, all three pieces of information will link back to the same quadratic relationship. Okay, so the first thing when we talk about the equation of a quadratic relation, um, it's since it's we're talking about the equation now, we've got a y equals in front. Okay, now if you remember grade 9, we talked about linear relationships. Its equation, linear equations, had the form y equals mx plus b. Okay, quadratic relation has this extra term in here, ax squared. Okay, the a can be any real number, meaning fraction, decimal, integer, except for 0. It can't be 0. Because if it was 0, it would be like it's not even there, and it would just be bx plus c, which is the same as a line. So what we're looking for in the equation is an x squared term that makes it quadratic instead of linear. Now, it can't have anything higher than a squared. If it did, it would be another type of relation. Okay, so it's definitely got an x squared term. It might have this term here, a constant times x, or just a constant, but b and c could be 0, so you might be just left with your x squared term. Okay, so we'll be looking at a lot in the next several lessons about these equations. Now the graph, if I was to graph, so we'll take a little peek here. This is a graph of a typical quadratic relation, and we have a name for this type of shape. Just like a linear equation had a line when you graph it, okay, a quadratic relation has, we call this a parabola. Okay, so a parabola is, well, the first thing about a parabola, it's very symmetrical. Basically, you can draw a line down the middle, and that's kind of like, you know, the point. It's a line exactly down the middle of this thing. And it's called U-shaped. Well, we like to throw this around a lot when we describe the shape. I kind of use this a little bit hesitantly because generally it looks like a U. And by the way, it could be an upside down U as well. So it can open up or down. But it's not really a U shape because a U, the sides go straight up and down on a U. But on this graph, it goes outwards to the right and outwards to the left. So it keeps going out. The more it goes up, the more it goes out. Okay. So that's what the graph of a quadratic relation looks like. The equation has this form here, ax squared plus bx plus c. Now there's a couple of new things. Let's look at the graph here. So we got a few things from the past here. We've got our y-intercept, which most relations will have. It's wherever that curve or the line crosses the y-axis. So in this case, we've got one of those. We also have x-intercept, but for this specific example, we actually have two x-intercepts. So that's different for a parabola. So basically a parabola, it definitely will have one and only one y-intercept, but the x-intercepts, it can change the number. You can actually have two, like is shown here. You could also have 1, and we'll talk about this later, and it could have 0, because if you think about it, if we move this whole parabola up, so the vertex is moving up along here, if the vertex was above the x-axis and it opened up, it wouldn't have any x-intercepts. Or if the vertex was right on the x-axis and opened up or down from there, it would only have 1 x-intercept. So for x-intercepts, we can have anywhere from 0 to 2. Okay, I think most of the graphs we'll see it's going to have 2, but definitely there's a chance it might have 0 or 1. Okay, now one thing I haven't talked about, I just mentioned that it can open up or it can open down like that, but it can never open sideways. It can never have a graph that looks like that. So that's a definite fact there. Now the other thing we haven't talked about is this extremely important point here called the vertex. So you can see why the vertex is important. In this graph, it's the very bottom. It's the most, it's the point furthest below on the graph. And you could also say that the vertex is when the graph changes from going down to going up. So it's that point where it changes direction. Okay. Now you could also have a graph that, opens down. A parabola that opens down like that. The vertex is still that point where it changes direction. This time it's where it changes from going up to going down, but it's still very easy to find. It's that point right in the middle, either at the very top or the very bottom of the parabola. Okay, so vertex is an extremely important point for quadratic relations, and we're going to talk a lot about it. So we've covered the vertex, the y-intercept, the x-intercepts. We also have this line. It's either called axis of symmetry or line of symmetry, really the same thing. You can see this dotted line. It's a vertical line and it goes right through the vertex. Okay, and that's called the axis or line of symmetry because the two sides of the parabola are basically exact copies of each other if we flip one side over to the other. Okay, and one important point that comes out from that is that if I, for example, these two x-intercepts, I've got one at 3, I've got one at -1. Well, where this line of axis of symmetry is, I can see that if I draw a line between the two x-intercepts, they're both 2 units away from the axis of symmetry. Okay, but it's not just the x-intercept that's true. If I looked at these 2 points down here, where y is equal to -3, okay, if I measure the distance from this point to the axis of symmetry, it's 1 unit from 1 to 2, and it's also 1 unit from axis of symmetry to this point. So, and that's going to be true of any point. I could draw a horizontal line through these points, these ones as well. And this one, in this case, this is 4 units from the axis of symmetry, and so is this. Okay, so symmetry is like the best example I think is a person's face. You could draw a line right down the middle of your face, and relatively speaking, the left side is usually a copy of the right side, but just kind of mirror image. Okay, so that's an important concept for quadratic relations and the graph of one. The parabola, very symmetrical, and that will actually be used as an important piece of information for figuring things out. So that's what a graph looks like. Okay, some new terminology there. Okay, so we got some key concepts here. Some of the stuff we've already talked about, so let's kind of go back through that. Relationship, the relation defined by y equals ax squared plus bx plus c is a quadratic relation. A relation is quadratic if the highest degree of the terms is 2. So we haven't talked about degree before, but degree is the exponent for any of the variables. So that would be a degree 2 term, that would be a degree 1 term. And a relation's quadratic if the highest degree of the terms is 2, and that's true with this equation here. And this I talked about. The graph of a quadratic relation is called a parabola. The parabola can open up or down, but never sideways. Okay, the vertex, which was that highest or lowest point, is the point where it changes from going up and going down. Okay, it's where it switches from one to the other, and the vertex is either the minimum, meaning the lowest point, or the maximum, the highest point on the graph. Okay, and then the parabola is symmetric about a line, vertical line that passes through the vertex. This line is called the axis of symmetry, abbreviated as AOS, because that's pretty long to write, or line of symmetry. Now this thing we haven't talked about yet, but if you remember back when we did linear relations in grade 9, you could look at the table of values and look at the first differences, and if they were all constant, you knew the relation was linear. We're going to extend that concept with the quadratic relationships. So with quadratic relation, the first differences are not constant, and that makes sense because if they were, it would be linear. But if you look at something called the second differences, and we'll do examples of this, the second differences are constant. So this is just kind of extending what we did with tables of values to determine if a relation was was linear or not. But now we're going to know, is it linear, is it quadratic, or is it something else? Okay, and we'll look at examples where we do that. Okay, so here I've got a series of equations, and we're going to determine whether the equations are linear, quadratic, or neither. Okay, so the first one here, y equals 2x squared plus 4x minus 7. Well, this lines up pretty nicely with the template we talked about at the beginning, ax squared plus bx plus c. Remember, a has to be a real number, like an integer, fraction, or decimal. But b can be anything, including 0. So we may or may not see these terms in the equation. But this matches up pretty close, because here the a is 2, the b is 4, and the c is negative 7. So this is definitely quadratic. Okay. The next one here, y equals negative x squared. Well, you know, we've got an x squared term, so it looks like it's quadratic, but it looks kind of short. But remember what I just said, the x term, and the constant don't have to be there, because they could be zeros. So that would be 0x plus 0, which means there's nothing there. So this is also quadratic. In this case, a would be negative 1, and b and c are both 0. So it may not have the same number of terms every time, but they can still be quadratic. It's got to have an x squared term though, okay? This one, y equals 8x to the power 3 plus 4x plus or minus 7. Well, the problem with this one, hopefully, is pretty obvious. The exponent needs to be a 2. That can be the highest. It can't be any higher than 2. So the fact that you have a 3 there, obviously this isn't linear either, because it's not mx plus b here. So that's going to be a neither. This one here, there's no x squared term, but there's an x term and a constant. So that is going to be our y equals mx plus b, so that's linear. This one's an interesting one. We've got y equals 3 squared. So you might think, well, there's that exponent 2, but it's important that the exponent is applying to the variable like x, not to a number, because 3 squared is really the same as 9. So the equation y equals 9, if you saw that by itself, you'd say, no, that's definitely not quadratic, but it is linear. In that case, it'd be like a y equals 0x plus 9. 0 would be the slope, so it's a horizontal line. Okay, what about this one? Well, again, no x squared term, but it has, you could fit this as y equals mx plus b, m is 12, b is 0. So this is also linear. Okay, now this one here, hopefully by now you'll probably guess that this is quadratic. It's got an x squared term, it's got an x term, it doesn't have a constant, but you could consider the constant to be 0. So in this case, the a is 1, the b is negative 30, and the c is 0. So definitely that's quadratic. Okay, here's an interesting animal. We've got y equals the square root of x. Well, anytime you see a square root, or we call this a radical sign, that's definitely not linear and it's definitely not quadratic. So that's going to be a solid neither or neither. And this one is most interesting, I think, because looking at that, you'd say, well, it sort of looks like linear and linear, okay, but it's really not mx plus b. It doesn't look like it's quadratic. However, remember when we did our expanding, we took two binomials and we expanded this. This actually turns into, when we expand it, y equals x squared minus 3x minus 4. And when you see it written that way, it's an obvious quadratic relation. So that brings an interesting perspective, because I didn't see an x squared there, but when we changed the way this looks by expanding it, we actually created what we consider to be a quadratic equation. Okay. Later on this unit, we're going to learn, well, that's a quadratic equation on its own. We just give it a different form. So we'll talk about that later on. Okay. So on this page, we're actually going to do our first graph of a quadratic relation. It says make a table of values for y equals 2x squared minus 4, and then graph the function. And then from the graph, state the vertex, the x-intercepts, the y-intercept, and the equation of the axis of symmetry. So what we're going to do here, we're going to create our own little table. So we've got our x on the left, y on the right. I'll actually put the equation in here so we remember. Okay, and then I'm going to have values x equals negative 2 all the way up to 2. Fill in the dashes. Okay, might as well put some lines in here too. Could be a little straighter. So what we actually do when we, just a refresher on making a table of values, we're going to plug in wherever we see an x, we're going to change it to the value in this column. So this one's going to be 2 times negative 2 squared minus 4. Okay, and we'll figure that out in a second. And just to get a little momentum going here, so we're just changing out what's in the brackets to the value of x in that row. 2 times 0 squared minus 4, 2 times 1 squared minus 4, and 2 times 2 squared minus 4. Okay, so if you're just starting off and you're getting used to this, let's start with a 0 and do the 1 and 2 and then go back and do the negatives. So in this case, we've got 2 times 0 squared. 0 squared is 0. 2 times 0 is 0. 0 minus 4 is minus 4. Okay, 2 times 1 squared, well, that's 2 times 1, which is 2. 2 minus 4 is negative 2. And then we have 2 times 2 squared, that's 2 times 4, which is 8. 8 minus 4 is 4. And then if we go back up here, if we change it to negative 1, you notice when we square a number, it's always positive, right? So I'd like you to take notice of this. 2 times negative 1 squared is the same as 2 times 1 squared, because these values are the same. They're both going to be 1. So that's 2 times 1 minus 4. That's 2 minus 4. And also the same thing here. This is going to be the same as what we did down here. So that's also going to be 8 minus 4, which is 4. So we've got these 5 points. And one thing I'd like you to take notice here, we talked about on the last page about the graph being symmetrical. That is, it's kind of the reflection on both sides. It's very similar on, so I can actually look at these values here. I've got a 4 and a 4, so I match those up. I got a -2 and a -2, and I got this -4. So not only is the graph symmetrical, but the table of values is also symmetrical. And the interesting thing we're going to find out is that guy that's in the middle there that doesn't really have a partner, that's actually the vertex. Okay? And it's kind of interesting we can figure that out without even graphing it. We're going to back it up with information from the graph. So let's put our points on. I'm going to put the supposed vertex on first. So that's 0, -4. And then I've got at 1, I've got -2, so 1 down here. And then if I go back to -1, I've got that mirror point. That's what we call these points. So remember how the points are exactly the same distance across from each other. And then for 2, I have 4, and -2, I also have 4. So 2, 4, and -2, 4 is up here. Okay, and when we're doing our sketch, okay, this is important. It was fairly easy to graph a line. You just do 2 or 3 or 4 points, get your ruler out and draw the line right down the middle of all the points. Well, this is a curve, and it has to look like a curve. It's not going to be connect the dots. Okay, so you have to put a little effort into this. It's not going to be perfect, but I want it to be a good effort. So when I'm drawing my parabola, or my graph here, I always start with the vertex. The vertex is the key point because it has to be a smooth transition. So I always do like a little U cup here first, and these have to be kind of pointing towards the next points. And then what I do is, I use my free hand, but I try to make it as smooth as possible. Okay, so it doesn't look like a, like I said, connect the dots. Okay, so that's not too bad. Make sure you do these with an eraser because sometimes your first attempt isn't always the best. So okay, so there's my graph, and you notice I put 2 arrows at the ends because just like a line, when you draw your line, it doesn't end where you drew your last points. It just keeps on going. So you see how I extended the line to fill up most of the graph up here. It's a little bit of guesswork, but it's intelligent guesswork. And then up here I put the lines. Okay, so that's a reasonably good attempt. So we did we graphed the functions. Now they want us to state the vertex, the x-intercepts. So let's just list these things we need. Vertex, x-intercepts. I'm going to shorten that. And then y-intercept. And axis of symmetry, I'm going to call AOS. Okay, these are going to be things that you should be able to pull off by just looking at a graph, and do it very quickly. Okay, so remember the vertex, that's the new point. That's kind of like the highest or the lowest point. It's the point where the curve changes direction. So I have to give both coordinates here. So basically deciding on the coordinates there, it looks a little confusing there with my dark line, but its x coordinate is 0 and the y coordinate is -4. And if I wasn't sure about that, I can see back in the table of values. 0, -4, we already knew that was going to be the vertex. And you have to put it in, because this is a point, right? You have to put it with a comma in between and brackets to show that it's a point. Because if I just put 0, -4, it looks like I'm listing 2 different things. Which I'll probably be doing with the x-intercepts. So let's skip the x-intercepts just for a second. Go to y-intercept. So y-intercept, that happens to be the same point that the vertex was. And it's just a coincidence. It doesn't always happen. But the vertex is, the y-intercept is at -4. Now if I wanted to put that as a point, I could. I'm okay if you guys just list the numbers for x and y intercepts, but if you want to put it in point coordinate form, that's perfect. So the y-intercept, the x-coordinate 0, and the y-coordinate's -4, very similar. It's the exact same point as the vertex in this case. And the y, let's do the axis symmetry. The axis symmetry, it's going to be kind of hard to draw this line because it's actually the same as the y-axis. Okay. So I just put a little bit to the left, make it dotted, don't make it dark. So I can't just say 0. I can't say the axis symmetry is 0 because 0 sounds like it's a point. So anytime I give the axis symmetry, it's always going to be a vertical line. So that means it's going to be, the equation is x equals, and in this case, it's going to be x equals 0. Okay, now here's something that could be quite useful. If you know what the vertex is, the axis symmetry is always x equals the x-coordinate of the vertex, because the axis symmetry always goes right through the vertex, so it has the same x-coordinate as the x values as the vertex. And if you think about it, that equation x equals 0, that every point along this line has the x-coordinate 0. The y-coordinate's always changing. So a lot of students will always try to skip this part about the x equal and just put 0, but you're going to lose some part marks on that if you do. Now the last thing is the x-intercepts. Now I don't actually have any points that I created from the table of values. So the x-intercepts would be here and here. So in this case there's 2. And remember we said earlier there can be 0 to 2 x-intercepts. So I'm guessing a little bit here because it looks like it's about 1.5 and -1.5. So I could put it like this, well, except that's a decimal, -1.5 comma 1.5, or I could list them as in coordinate form. So if that's, that would be -1.5 comma 0 and 1.5 comma 0. Either one's fine. For the x and y intercepts, you could just list the values, or you could list the points. You notice the x-intercepts, the y is equal to 0, and the y-intercept, the x is equal to 0. That's how we find them a lot of times from the equation. Okay, so there's a little exercise. Take an equation, build a table of values, graph it, and then pull out the key information from it. Okay. Eventually, we won't have to graph it to get this information. We'll be able to do some other things and figure out all these values. Now, the last thing is the looking at the table of values. So in this case, we're going to look at these 2 different tables of values. For each one, we're going to look at first and possibly second differences and determine, using that first and second difference information, whether this is a linear or quadratic relation. So hopefully the first part will remind you from grade 9. So you just kind of add yourself another column to the right. Okay, I'm going to call this first diff. Okay, now if you remember the differences, I was basically subtracting a value from the next value. So how much did it change going from 6 to 8? So it's always the number that's lower on the table, subtract the one above it. So when I do mine, and this is kind of up to you, I do my rows a little bit staggered. So I draw the actual line halfway between the previous lines, and then I'm just shading in the top and bottom, because if I have 5 points, which I do here, I'm only going to have 4 first differences, okay, because I need 2 y coordinates to make 1 first difference. So when I do my math here, so this is 8 minus 6, which is equal to plus 2. I have 10 minus 8, which is equal to plus positive 2. 12 minus 10, and you can see the pattern already here, positive 2, and then 14 minus 12 is positive 2. And this might have been something you did last year. We look at these values here and we notice they're all the same, which another way of saying they're the same is that they're constant. Okay, so from here we can conclude the first differences are constant. So the relation is linear. Okay, so like I said, that could have been a question you had last year, and we didn't have to look any farther because we knew it was linear. So probably got a good feeling this won't be linear, and you can probably just look at these values and know that without. Okay, oops, I didn't want to do that. Okay, so remember I do my staggered horizontal lines here, and then I'm going to shade in the top and the bottom. Okay, and call this one first diff for differences. And then this time it's 7 minus 10, so that's equal to negative 3. 6 minus 7, that's equal to negative 1. 7 minus 6, and you can see the order is very important. Okay, that's going to be positive 1, and then 10 minus 7, that's going to be positive 3. And you can see they're not constant. Okay, so what we have to do now, what we can conclude at this point is this is not linear. Okay, but we don't know it's quadratic until we test the second differences. So again, we do another column, call it second diff, and then we're going to split our previous rows down the middle. Okay, and this time I'm filling in a bigger space. So I've gone from 5 points, 5 rows, or 5 points here, to 4 first differences to 3 second differences. Every time I do this process, I lose a row. Okay, so this time instead of looking at the y values, we're looking at how did these change. So in this case, it's minus 1 or negative 1 minus negative 3, which is plus 3. That's equal to positive 2. Okay, here I've got 1 minus negative 1, which is again plus 1. So that's positive 2. And then 3 minus 1 is also positive 2. So this time we notice that the second differences are constant. So we can conclude that this relation is quadratic. So relation is quadratic. Now, remember when we were doing first differences, the actual number here didn't really matter. Well, actually, we learned later on that this is the slope of the line, but to determine if it's linear, it didn't matter what the number was here as long as they're all the same. So that's also true second differences, and it's just a fluke that these happen to be the same. There's really no connection at all, that they're always going to be plus 2. That's definitely not the case. Okay, so now we have a tool. If I give you a table of values, that you could do first and second difference test and be able to proclaim that this is linear or this is quadratic. Now, what would happen if this wasn't constant? Well, all we could conclude would be that this relation is not linear or quadratic. It's something else. It's some other relation, okay? Which definitely, everything's not linear or quadratic. There's definitely more types of relations that are out there that we haven't looked at yet. Okay, last page. So this is a word problem. We're going to be seeing a lot of these at the end of the unit. Okay. Now, we shouldn't get too caught up in the words. but we should be extracting the important math information here. It says each arch, now just so you know, an arch, like the golden arches, arches are parabolas. They're structures that are shaped like parabolas. We call it parabolic. So there's some structures in this building that are arches inside the building, and somebody took some measurements and decided that you can actually build an equation that will model the exact height and distances on this arch that's inside here. And that equation is y equals negative 0.5x squared plus 26. Y represents the height, x is the distance, the height in meters, and x is the width in meters. How far is it away from the center of the hallway? Okay, so we've got to graph it first. So the graph's already here for us. Now I'm not going to put on any scale until I actually get some values. So I'm going to make I didn't really leave a lot of room for a table of values, but that's something we have to do. So I'm going to put my x and y values here. So I'll just remind myself of the equation above here. And I'm going to go from -8 to +8, but intervals of 2. So -8, -6, -4, -2, 0, 1, or sorry, 0, 2, 4, 6, 8. And a lot of values there, but it's going to help us graph this a little better. So I always like to start with 0. If I plug in 0 in here, that turns to 0, and this is 26. Okay. If I plug in a 2, I get 2 squared is 4. 4 times -1/2, that's -2, plus 26, that's 24. And here's where the symmetry comes in nice. That's 24 here. If I plugged in -2, I would get the exact same value, because when I square -2, I also get 4. So those two values are the same, and you can see the symmetry coming out here. Okay, and then I've got, if I plug in a 4, that would be 4 squared is 16. -1/2 of 16 is -8. -8 plus 26 is 18. And again, I'm going to get the exact same value for -4. And then for 6, I'll just go to the final answers. I get 8. I also get it for -6. And then for 8, I get -6. And also for -8. So what I can do now is decide on my scale. So the first thing I notice, I don't have, my y values. The highest is 26, the lowest is -6. So I'm going to have to fit 26 on here. So it seems like maybe I should go up by 5s for this scale. 5, 10, 15, 20, 25, 30. And that should fit all the positive values. And then down here, I got to be able to fit -6. So I'll go down to -10. Okay. And then for the x scale, so remember I picked values between -8 and +8. So I can't go up by 1s because I won't be able to fit everything on, but I'll go up by 2s. So 0, 2, 4, 6, 8, 10. And then negatives as well, -6, -8, -10. Okay, and now I'm going to plot my points. Okay, now remember we were talking about symmetry, right? So we've got our matching y coordinates, and I said that that would be the vertex in the middle there, with 26. So 0, 26 would be right about there. And based on this, it looks like that's going to be my highest point, which is also my vertex. Okay, and then I'll go start doing the other points. So at 2, I've got 24. And I've also got 24 over here. We call those mirror points. And then at 4, I've got 18. So that's about here. And mirror point over here. And then at 6, I've got 8. 8's about there. Okay, and then at x equals 8, I've got -6, just below here. And I've also got -8, -6. Okay, so there's my, and you can see the shape. It looks like a parabola, and that looks like the vertex, which we've. So I'm going to do my sketch, and I like, do a nice free flowing graph, and then same thing over here. Now, by definition, if I was graphing this equation, it would keep on going forever, right? It would keep going down and down. But we're thinking about this arch that's inside a building. So when it hits the x-axis, that's basically the floor. So I'm looking at this from the side. The arch goes up in the air, comes back down. It basically stops right here. I mean, there might be part of it that's underground for support, but we really don't see this. So I'm not going to put arrows in this situation because it doesn't really go on forever. It doesn't go into the basement of the building or the parking garage. It probably stops very close to the floor that you see. That's my graph. It looks pretty good. I do say so myself. Now, a couple of questions down here. Describe the shape of the arch. Well, we knew this was a quadratic from the equation, and we know quadratic relations have parabolas, and we've confirmed that with the actual graph. So the shape is a parabola. And please learn how to pronounce this right. It's not parabola, it's parabola. And you could say something has a parabolic shape. Okay, parabolic IC at the end. And we could also say, just to clarify, it's opening down. Okay, how tall? Well, we'll start with this. How tall is the arch? Well, if that's the floor, it goes up to a maximum height of 26 meters. So the height is 26 meters. Sorry, height is equal to 26 meters. How did I know it was meters? Well, from the description, it said y is the height in meters and x is the width in meters. Okay, so putting just 26, that's not good enough. Okay, because it could be kilometers, could be millimeters. I want to know exactly how high that thing is. And then the width. This is a little bit trickier. Okay, so the width, I could say so again, just like the last graph I did, I don't really have the exact values where the x-intercepts are, but it looks like it's pretty close, somewhere between 7 and 8. So what I want to do is how far is this whole width here? So this is the width along here. So I know it goes from 0 to this value and 0 to this value, but these two values are the same. One's just negative, right? So it's basically double this distance here. So when I graphed this on Desmos, I got a more accurate value. It wasn't too far off from what I had here. I had 7.2 was here, so it would be 7.2 here, negative 7.2 here. So the width is going to be equal to 2 times 7.2 meters, which is equal to 14.4 meters. So that's pretty good. We figured out the height and the width of this actual, and this is approximately, by the way. Yeah, so we were able to find out the width and the height of this arch just by its equation. Okay, and like I said, you'll be developing skills so that you'll be able to work with just the equation and get the same information, and not have to graph it. I mean, you could always graph it and figure this out, but that might take quite a bit of time, as you just saw. Okay, so I got some homework questions here for you. Now, please note this one here, page 195, 6, and 7. This is from a future section, but it's got a bunch of graphs that I just want you to look at, and all I want you to do is what we did with example 2, or maybe it was example 1, I'm not sure, where you state the vertex, the x-intercepts, the y-intercept, and the equation of the axis symmetry. So ignore the questions for 6 and 7 here. They're asking for something that you probably don't know how to do yet. I just want you to look at the graph and pull out this information. Okay. Some of these questions earlier, they're more about tables of values, determine whether a relation is linear, quadratic, or neither. I think 5 is an application question, so it's not as bad as it looks when you see all this writing here. Okay, so have a good attempt at that, and we'll see you on the next math lesson on quadratic equations. Have a good day.